Hello. This lecture will cover pages 192 through 194 of my lecture notes. Please print those pages out and have them in front of you as I present this lecture on Chapter 12D, Frequency Response Using Bode Plots, continued. If you remember, in the last couple lectures, we went through how to handle the different terms in the transfer function. I showed you how to handle that single K0 term, and I showed you how to handle these single S terms, either in the numerator as a 0 or in the denominator as a pole. This lecture shows you how to handle these first order terms, either in the numerator as a 0 or in the denominator as a pole. And once we get through this, we'll be able to work the problems out. The 10 problems that I have for you. Now these problems are going to be easy. I could have went straight to the problems. I think you could have worked them out directly, but you wouldn't have understood why we're using the rules of thumb that we're using. This last lecture and this lecture will help you understand why we'll be able to use some of the rules and techniques that makes Bode plots pretty simple to graph. We're going to look at case 3 now. The case 3 show you the single first order terms either in the numerator or denominator, either in a time constant form, and this we call it our time constant form, or in the break frequency form, and we call this our break frequency form. Okay. First of all, we're going to look at 0 example, and the simple example we're going to look at is s plus k to the 1, where this could be, let me show you what I mean here. Here's one. Forget about the constant term now. S plus 100. Or here, S plus 10, or the S plus 200. These are all first order terms in the numerator. How do you handle those terms? Well, we're going to let n equal 1. And I'll make a simple observation with if you have the second order or the third order on to each of those terms. T of S is equal to S plus K, where K can be a constant. That's the break frequency form. We know we have to get that break frequency form into the time constant form. We've done that before. T sub S is equal to K. That's going to be our K0 in this case. Tau S plus 1. Where we know tau, okay, we know S is the j omega. I just rearranged this here. J omega tau is the same as tau S. Don't forget S is j omega. We already know how to handle the K term, so let's just look at this term right here. Let's just look at that j omega tau plus 1 term. How do we handle that? Well, the dB is 20 times the log of the absolute value of that, which is 20 times the log of 1 plus j omega tau. That's it, right there. That's the complex number. It's 20 times the log of that number. Now, for omega tau being much, much less than 1, for this value here being much, much less than 1, or another way of looking at it is omega being much, much less than the break frequency. And we're getting that simply by, look here, we're getting that just by letting this tau go over on this side. And we know that omega is equal to 1 over tau. That becomes the break frequency. 1 over tau is the break frequency. So for the break frequency being much, much less, for this omega being much, much less than the break frequency, it's the same thing. This term here goes away and you end up with just the 1 for a gain. Well, dB is 20 times the log of 1, which is 0 dB, and it's a real number, you get 0 degrees. So when you're much, much less than the break frequency, in this omega axis right here, when you're much, much less than this break frequency here, you're talking about a 0. The angle associated with this down here is going to be 0 degrees for that reason. What about when omega tau is much, much greater than 1? What about when this term here is much, much greater than 1? Another way of looking at that, if you think of omega is equal to, or 1 over tau is equal to the break frequency, another way of looking at that is, what if the omega is much, much greater than the break? What if omega is much, much greater than the break frequency? Well, then this term here overshadows the real number here. And you end up with dB is equal to 20 times the log of j omega tau. Well, that's the same as case 2. That's just the same as case 2. J omega is S. You have a single S term. So you know if it's a 0, it's breaking up at 20 dB per decade. And you know the angle's always going to be 90 degrees. What about the case where omega tau is exactly equal to 1? What if this omega tau up here is equal to 1? You get 1 plus J1. In other words, what happens right at the break frequency? Well, dB is equal to 20 times the log of 1 plus J1, which is 20 times the log of the square root of 2. That's 3D. That's your 3 dB point. And the angle associated with this, I think you can see, is 45 degrees. So what's that telling you? This is what it tells you. When you have a 0, and this is your break frequency, when you're much, much less than the break frequency, the angle is going to be 0 degrees. Right there. That's 0 degrees right there. When you're much, much greater, the angle is going to be 90 degrees. When you're much greater than that break frequency up in here, you're going to be at 90 degrees for every single 0 of that form, tau s plus 1. In between, when you're halfway, when you're at the break frequency, when you're right at the break frequency, you're going to be at plus 45 degrees. Now, what do I define as much, much greater and much, much less? I take my break frequency and I go 1/10 of it and I put an X on my Bode plot. Then I take my break frequency and I go 10 times it and I put an X. So one decade below the break frequency, I'm going to assume the effect didn't come into effect yet. You're at 0 degrees. At 10 times the break frequency, it's going to have full effect. So you're going to be at 90 degrees. And in between, you're going to be at 45 degrees. And that's how you plot these. You already know how to plot these magnitudes. We talked about that. What about the phase? Well, that's how you do the phase. And I want you to notice that these lines I drew out to the break frequency, and then it's a 0 that goes straight up at 20 dB per decade. That's that single S term I was talking about. Whenever the j omega overshadowed the 1. Well, the actual curve is asymptotic to these lines. It approaches this line here, and if that's 0 dB, the actual curve is asymptotic here. It's right at the break frequency. You're exactly at 3 dB up. So for zeros, you're always a little bit above. You're 3 dB above where the linear lines for your approximation come to. So if I asked you at the break frequency, what's the gain of that circuit? It's going to be 3 dB. Because that's the actual curve. And then it's asymptotic to this straight line approximation up here. These Bode plots are just straight line approximations. If you have two of these, if that's squared or that's to the third power, the only thing that's going to happen is that you know this is going to break up at 40 dB per decade if there's two of them. And this angle is going to go to minus 180. 0, minus 180. In between, you're at plus 90. That's how you handle those terms. What about the pull example? S plus k to the minus 1, where it's in the denominator. We're going to let n equal 1 again. As we did for the 0 example, a straight line analysis results in the following plot. T of s is equal to 1 over s plus k. Well, let's make that 1 over s plus 30. I don't know, whatever. Make something up. Okay, that's what it looks like. And how do you get that? I think we looked at that before. We worked it out. We looked at it. Matter of fact, That was this circuit right here. This is one of the first circuits we're going to work with, but there's that circuit right there is going to lead to something that looks like this. Look at that. Look at that. So the straight line approximation of that is, if you go through the same analysis that we did, except don't forget, this is a pull example, and you have a -1 as an exponent up here, at the break frequency, right at the break frequency, when omega is exactly equal to the break frequency, you're going to be at -45 degrees. A decade down from the break frequency, you're going to be at 0. And a decade up from the break frequency, you're going to be at -90 degrees. So whereas zeros always do this with frequency, you know, single zero terms always break up at 20 dB per decade, and they go from 0 to +90, 45 degrees at the break. If you have a pole, it breaks down at -20 dB per decade. At the break frequency, it's at -45. A decade down, it's at 0. A decade up, it's at -90. And if this is a squared term, you just have 2 of these here. But the way you handle that is, it breaks down at -40 dB per decade. Break frequency, it's going to be halfway between 0 and -180, which will be a -90 at the break frequency. So that's how we're getting our magnitude plots, and that's how we're going to get our phase plots. So all we do from this point on, that's a 12-minute lecture so far, but all we do from this point on is I just show you examples. We work example number 1 through example number 10, and I have like 4 or 5 homework problems for you to work on. So this is where you're going to have to get your graph paper out. And this I think this is fun because you get a lot of insight into this. And you're going to use this in your controls class. You're going to use this in another op-amp class you're going to see later. So hopefully you can download these last couple lectures and have them handy to look at later on, because I've had people tell me that these 4 lectures really helped when they got to their Bode plot frequency analysis in future classes. But you need to get some log paper. So that log paper, I showed you what it looked like. You want to download that from Canvas. I have posted on Canvas. So get about 10 copies of that downloaded and printed out. And get that straight edge and a couple sharp pencils ready, because the next 3 lectures, I'm going to take my time with it, but we're just going to work problems out and make sure you understand how to do Bode plot analysis. And that concludes this lecture.